Hello. Thanks everyone for coming. Please excuse me if I'm a little bit nervous. I'm a programmer. I'm not used to speaking in front of people. I gotta turn on my computer here. All right. We're going? Okay, great. Again, sorry. My name's Boodman. I'm an engineer at Google. I work on the Gears project, which Alan just told you about. And I'm very excited to be here. This is the very first announcement of Gears anywhere in the world here in Australia. They flew me in from Mountain View to talk to you guys about it. So thanks for that. Basically, Gears is a tool to enable you to write web applications that can run offline. Before I go into this presentation, is going to give you a little bit more detail about why we built it, what our motivations were, and I'm going to show some demos and some code and stuff like that. But before I do that, I want to talk a little bit about why we even decided to do this. So I'm sure there's some bloggers here. You may have read some recent discussion about why we even need web applications. And so I want to go into some background about why we think we need that. So the first reason when we were thinking about building Gears and taking applications offline that would be useful is for reliability. Even Google, with our fantastic uptime, is occasionally down. And for web applications to be really useful, you have to be able to depend on them. You have to be able to know that when you go to get a piece of data, it will be available no matter what. And having web applications that can run offline would really help that. For example, if you're a salesperson and you go to give a presentation, you don't want to rely on a piece of data that could be on a server that you might not be able to access. You want to know for sure that you can get it no matter what. And so reliability, I think, is a key issue why you want to have web applications that run offline. Another thing is performance. Having applications that can run offline obviously allows you to run them when you don't have an internet connection. But another great reason is because if an application can run offline, that implies that it has local data, and therefore it could run much faster. Local acceleration, performance is another reason we want to support offline applications. Another reason is convenience. People talk a lot about how broadband penetration is getting better and better, and broadband is everywhere, and why do we need offline applications? Because soon you'll be able to have broadband on a plane, you'll have it wherever you are. But a good example of why this isn't working and why you still need offline applications is me traveling here. I'm staying at the Sydney Hilton, which is a very fancy hotel that has broadband. But every time I want to use it, I have to go through this 10-minute setup process to type in my password and put in my credit card information. And sometimes it doesn't work, and there's proxy configuration issues. And if all I'm trying to do is get a phone number of someone I'm supposed to call or get the address to something, I don't want to have to go through this 10-minute rigmarole to get this data. If my web applications could run offline, then I could just get that data without having to get an internet connection, and that would be much more useful. And finally, we think you're offline a lot more than you think. We think maybe people are used to the fact that you can't use the internet in certain contexts, and so they're just thinking, well, of course you don't have internet on a plane. Of course you don't have it on a train when you're on your way to work. Of course you don't have it in these contexts. And I think if we made applications available to work offline, you would find that you're offline more often than you think. So having our motivations in place, knowing what we wanted to build, that we wanted to somehow enable web applications to go offline, we thought, OK, ignore resources, ignore technical constraints. If we just think about what do we want, how do we want this thing to work, how do we want it to work in a perfect world, what features would we want, how would we want web applications to work? So we thought about our Google products. How do we want those to work if they work offline? And so the first thing we thought of was, we want there to be one URL. If you're using reader.google.com and you want to use it offline, you should just go to reader.google.com. You shouldn't have to remember that you need to use the special offline version of Reader. Similar with any other application. There shouldn't be a special version that you use when you're offline. It should just be the same app that you always use with no differences. Another thing we wanted to support was seamless transitions between online and offline. So Outlook actually does a really good job of this. If you've ever used Outlook, you can turn it on when you're offline, you can turn it on when you're online. It works the exact same way. And you can transition between connected and disconnected really easily. And that's the same sort of application that we wanted to support with this technology. So we knew that was one of the key things that we needed to support. Another thing was the ability to use local data. Again, going back to performance. Think about how much faster applications seemed when AJAX came out. all of a sudden these applications seem much faster, but the internet connections didn't change. What changed was that you were transmitting less data. And so now the applications are much more responsive because they don't have to transmit the entire UI every time something changes. So now if you had local storage, you wouldn't need to transmit any data for many types of tasks. So if you have all the data locally, there's many types of views in your application that you could show, many updates that you could do without having to transmit any data to the server. And that would make applications much faster. And finally, as long as we're dreaming about things that we would want in a perfect world, we want it to work for everyone, on every browser, every operating system, no matter what they use. We want it to be available to everyone. And a pony. So how are we going to do this? So now we knew, OK, this is what we want. These are the features we want. And we started thinking, OK, what's this going to look like? Well, there's many different ways to build applications today. And we wanted to figure out where is Gears going to fit in the spectrum of applications. And so on one side, you have AJAX applications that have lots of advantages. You can update them immediately. If there's a security problem, you can fix it instantly. But they have very low capabilities. They can't access local hardware. They don't have 3D acceleration, and so on. And on the other side, you have native applications that have their own pluses and minuses. They have access to the hardware. They can run very fast, but they have lots of requirements to what kind of software they need on the client. So we thought about it, and we thought, well, we know that AJAX applications have a lot of downsides, but we're very comfortable writing AJAX applications. We think they also have a lot of positive aspects, and that's where our expertise lies, and we really believe in the web. And so we thought, well, the way we're going to build Gears is we want to add just enough to AJAX to make it work offline. So it's an incremental improvement. We're not trying to redesign how the web works. We're just trying to add new features to the web, just enough new features to make it work offline. So Gears is an incremental approach, is what I'm getting at. And specifically what it is a browser plugin. It's a browser plugin. In Firefox, it's an extension. On Windows, it's a browser helper object. On Safari, it's a plugin. And we are supporting, as I said, as I have here, initially, IE, Firefox, on all the platforms that Firefox supports. And we're also supporting Safari, although the Safari binary is not shipping today. But if you're a developer, you can go and check out the code. You can build it, and you can run it on Safari. It's completely open source, as Alan mentioned. We knew that if we wanted this to work on all platforms for all users, even Google doesn't have infinite resources, and we couldn't write this for every single browser on every single operating system. We did our best, and we did a pretty good job. But in order for it to be available to everyone, we knew it had to be completely liberally open source. So we chose a very liberal open source license called NewBSD, which basically means that you can do whatever you want with the Gears source code. And we released it very early. This is an early beta release. It has some rough edges. We know it will crash occasionally, but we want to get feedback. We want you to start using it. We want to play with it. We want to know where it works, where it doesn't work, and we want to iterate very rapidly. So join the discussion groups and let us know how it works. So that's sort of like the fluffy high level, where do we come from? Now I want to look at, in more detail, how do we want these Gears apps to work? What's the architecture of them? So I talked about how we want these applications to transition seamlessly from online to offline. And in order to do that, the way you have to write your application, we discovered, is basically you use some sort of local storage as a buffer. So in typical AJAX applications, you read and write. When something happens in the UI, you send a request to the server immediately. So if someone clicks on a button, you send a request. When you want to view something, you send a request. When you want to write applications that work offline, you need to have a local buffer. So instead of talking to the server, you ask the database for the data. So you immediately ask the database for the data. And when someone clicks on a button to update something, you update the database. And then separately from that, on sort of a separate background process, you periodically check the database to see if any changes have occurred. And if any changes have occurred, then you send those to the server when you can. So basically, you need to decouple the server communication from the UI. So I want to show like some, your basic architectural diagrams to show. I think the pictures are probably easier to understand. So this is a very incredibly basic diagram, of how AJAX applications work today. I know there's many more pieces in AJAX applications. I'm not trying to say that they're all made of 3 boxes, but these are the pieces that we're concerned about. So basically, you have a UI. It has some elements in it. And when stuff happens in the UI, you use XML HTTP request to talk to the server, get information to show to the user. And when you want to change something in the UI, you use XML HTTP request to tell your server about the change. So how does a Gears application differ from that? So in a Gears application, it's sort of the same. You still have the same UI. You still have that blue box over on the side. But now, when something changes in the UI, you talk to the database. When you need to get data, you talk to the database. And separately from that, in the background, you have some code, some synchronization code that periodically checks the database to see if there's changes. And if there is, it uses a similar XML HTTP request type code to talk to the server. And this is how you can transition seamlessly between online and offline. Because if you're offline, that local database is still there. The code still works. It can still read from the database. It can still make changes. And just the synchronization code will stop working. And then when you get an internet connection, that synchronization code will start working again seamlessly. And all the changes will be sent to the server. So there's still another way to look at this. I don't know if you guys remember when AJAX first hit the scene and people discovered AJAX. This diagram was floating around a lot. And it was a way that you could sort of explain to managers and salespeople what AJAX meant. And basically, this is the traffic patterns of an old-fashioned web application, pre-AJAX. So every time something happens in the UI, every time there's a user action, a request is sent to the server. So this makes it very slow and unresponsive, and it's no good. So this is what happened when we added AJAX. Now, a lot of the user actions don't need to go to the server. The UI can respond to them itself. And also, a lot of the requests that go to the server are much smaller. So with Gears, almost all the requests stay local. You have the data locally. You have a local storage. So you really don't need to go to the server that often. And when you do go to the server, it's completely disconnected from what's happening in the UI. So this makes applications much faster, much more responsive, and obviously they can continue to work when you're offline. So we got to the point where we knew what kind of applications we wanted, how they were basically going to work, and so we started to think, OK, what actual APIs do we need to support these types of applications? And again, we were trying to go for isolated strategic improvements to the browser instead of redesigning everything. So we wanted, what are the key APIs that we need to take applications offline? And we came up with 3 sets of APIs, and we call these modules. So Gears today is shipping with these 3 modules: a local server, which enables you to start your applications offline and run them when you don't have an internet connection; a database, which allows you to store large amounts of structured data in a SQL database; and worker pool, which allows you to run long-running IO-intensive or CPU-intensive processes in the background without blocking the UI. And now I'm going to go into each one of these APIs in a little bit more detail, show you how they work, what the code looks like to use them, and give you a few demos. So first, like I said, there's the local server. So if you're going to run an application offline, a web app offline, the first thing you need to figure out is how to start the thing, right? Like you open up your browser, you type in reader.google.com, and nothing happens because you don't have an internet connection. So how are you going to start it? So local server solves this problem by adding 2 specialized caches to the browser. So web developers today are probably familiar with the browser cache, which makes it so that every single request for a resource doesn't have to go to the web. But browser caches aren't under the control of the application. The browser is allowed to just evict things from the cache whenever it wants. And it also periodically checks the web to see if the resource is updated. And if you want to run an application offline, you need to be sure that the resources that make up your application are always available. So that's why Gears adds these specialized caches. And there's actually 2 different types, like I said. One's called Resource Store, and one's called Managed Resource Store. And the Resource Store is optimized for capturing individual arbitrary URLs. And the Managed Resource Store is for capturing an entire application. And I'll explain what that means a little bit more. So when we started, we thought, OK, you want to run an application offline. Applications have JavaScript, CSS, images. We need to capture those things and serve them offline. And so we designed this API, the capture URL. You give it a URL that you want to store offline. It tells you when it's done. And this was good. And we're like, great, we're done. We can run these things offline. Move on. But what we found is that it didn't work exactly right. There's lots of cases where you need more than this if you want to run an application offline. So one of these problems is, let's say that you're in the middle of capturing all the URLs that run your application. And you get to, there's like 10 URLs in it, and you get to the 5th one, and you unplug the internet cable. Now what happens? You have half the resources that make up your application offline and half of them not offline. Now, if you have one JavaScript file, if you have 2 JavaScript files, for example, in your application, and they depend on each other, you have different versions running at the same time. So basically, this can't work for robust applications. And we needed some way to atomically swap in a bunch of URLs at one time. So capture a whole bunch of URLs at once that make up an application, and don't enable any of them until they're all captured and ready to go. So that's why we created the managed resource store, which does exactly that. Instead of, managed resource store is different because instead of telling it capture this URL, capture this URL, capture this other URL, you give it the URL of a single file that lists all the URLs that should be captured. And this file is called a manifest, and it's just a list. It's just a list of all the resources that make up your application. But the key thing is that this resource is not part of your application; it's separate. And so Gears can periodically check this manifest and see if any of the resources have changed. It can check to see if it should update, and also it can grab all these things atomically and make sure that they're all enabled at the same time. Another really good thing about Managed Resource Store is it solves the problem of an application getting wedged. So one thing we really worried about when we were working on Gears was the auto-update problem. Basically, if you have the previous API, the Resource Store API, and you have a JavaScript file, and I know this is probably silly to think about because no one writes code with bugs. I certainly never write code with bugs. But if you accidentally were to push a JavaScript file that had a problem, and it couldn't call the resource store update URL API, it couldn't call the capture URL API, then your application would be stuck. It could no longer work because it couldn't call that API. And so one of the things that Managed Resource Store solves is by giving Gears the location of where all the resources are listed, Gears can periodically check that list all by itself. It doesn't need you to call any function. And so once you set up a Managed Resource Store instance, Gears will, every time the Managed Resource Store is used, it will check to see if it's up to date. And if it's not up to date and it has an internet connection, then it will download all the resources and make sure it is up to date. So it basically makes it so that no matter what you do, if you push a totally broken version of your application, you can fix it, just like on the web, which is a very important feature. So I don't know how, maybe this hasn't been clear, but I wanted to show some code because as a developer, I think it's easiest to understand how these things work by seeing code. So this is basically how you interact with the local server module. First of all, you access all Gears modules through this special object called the factory. And the reason why we do this is because we expect that we'll change the way that Gears works over time. And having a single object that you access all of Gears objects through allows us to change our underlying implementation without breaking applications. So it's really important that you always use the factory object to access Gears. And then you tell it the name of the module that you want to access. In this case, it's the local server. And you tell it what version you want. And the versioning scheme is going to work similarly to other versioning schemes you may be familiar with, namely that minor version number changes are non-breaking. So if we release version 1.1 of local server that has some cool new features, you can use it with code that was meant for 1.0, and that's OK. But if we decide, well, the implementation of local server that we have really stinks, and we need to do a new one, we'll call that one 2.0 because it's a breaking change. And you wouldn't want to use that with code written for 1.0. So once you have a local server, this is a Managed Resource Store demo, so you create a Managed Resource Store. And then the key part is that you give it the URL of a manifest. So this is the place where all the files that are part of the application are listed. And then you tell it to check for updates. And then once you've done this, from that point forward, Gears will automatically check that manifest from time to time to make sure that it's up to date. And here's an example of what the manifest looks like. It has a version, which is how Gears knows that it has changed. So when you change your application, you change this version number. And then it lists all the resources that are in the application. So this is a very simple application that has only 3 resources. But you can have as many as you want. And basically what happens is when you request any of these resources, Gears will serve it immediately so that it can work offline. But then it will spin off a separate process to go and fetch this manifest and see if the version number is different. If there's any different version number in there, then it will re-request all these resources and make sure that it has the most up-to-date version. So demo. So you may be noticing here that this presentation is a little bit different style than your typical PowerPoint. This is actually a small web application that I wrote to demonstrate Gears. And I thought it would be cool, since Gears is about taking things offline, to actually take this presentation offline. So I'm going to do a major presentation no-no here and unplug the network cable and see what happens. So when I click this link, it's going to run some code that's really similar to what I showed on the previous slide. and it's going to set up a manifest. It's going to download all the resources, and then I should be able to go offline and continue with the presentation. So here we go. It says it's capturing. It says it's captured. So I unplug. I get the little thing that says I'm now offline. And just to prove there's no fooling, I will clear my cache. I did this presentation like a bunch of times for practice, and every time I forgot to clear the cache, and then I'd like go to google.com, and it would show up, and I'd be like, oh. Anyway, so now I can go to google.com, and it doesn't work because I'm offline, which is what you'd expect. But I can also refresh this thing here. I can go back. I can see previous slides. And now this presentation is running completely offline with Gears. Thank you. So that's the local server. So that's great. Now you can start your application offline. You can type in the URL of your application, and it runs offline, and that's good. But as soon as you have that working, you have another problem, which is now you're making changes to your application while it's offline, and you need to store those changes somehow. So you need local storage. And there's been a few different ideas on how to do local storage, but we're Google, and we like to do things big. And so none of those options that are available today have really large local storage. And so what we decided to do was add a full local SQL relational database to the browser. And we looked around to see what options there were, and we found SQLite, which is a very small 340K DLL, open source, mature, fully featured relational database. So it has indexes, keys, you can do joins, everything that you'd expect from a database. And being web developers, I'm sure you're familiar with using databases. And that also makes it really cool because there's nothing new to learn. So if you've ever written any database code on the server, you can write database code for Gears. And like I said, it scales very well. It has up to gigabytes of storage capacity. It's really only limited by how big your hard disk is. And we've implemented it using a very strict same origin security policy. Basically, applications can only open databases that were created by pages that are part of the same domain, port, and protocol. So here's an example of how to use the database. Again, you use the factory object to get started, or you use the factory object to create the module that you want. You give it the name database. All these module names are prefixed by beta right now because, again, this is a beta release, an early release. And once we get your feedback and we iterate a little bit and we find out where we've gone wrong, we will make this a final release and we'll remove the beta names. But we're just leaving the beta names in for now to make it really clear that this is an early code and we want feedback. And then once you've got your database object, you call execute. You pass it some SQL. If you've ever written code with a database, this should look familiar to you. And in this example, we're apparently managing a list of delicious foods. And so we insert burritos, which are yummy, into the list. And then we execute some SQL to pull out the list of delicious foods and order them. And again, this is just standard SQL code. And then we can iterate through it using the result set object and output the names of the fields. So I'm not going to go into this in a lot of detail because I think most developers, this looks very familiar to you. This is all documented in our SDK, which is live today. And so you can go and read more about it. The only thing I do want to mention is that you may notice these question marks in the insert statement. And the reason why this is here is for security. When database programming on the web first came out, a lot of people learned the hard way about SQL injection attacks. And this is basically parameterized SQL. So you put the question mark where you want your data to go, where your parameters are. And then separately, you pass in the parameters. And Gears does all the escaping to make sure that this goes in safely. So although you can concatenate strings of SQL together, you really shouldn't. When at all possible, you should use parameterized SQL for safety. So now I can give another demo. So I mentioned that this presentation runs offline, but what's also cool about it is that it's written like any other web application. It's database driven. So I don't have 25 HTML files here that all look the same that are running offline. What I have is one HTML file that has a bunch of slots in it where data goes, and then I store the points for these slides. These points I have here and the titles of the slides are stored in a database. And then I populate the slide template dynamically from the database. So I can show you how that works. So what I'm opening here is a tool that comes with our SDK. It's the database query tool. And this should look familiar to you if you've worked with a database again. It's basically a command line for your database. So this query that's in here right now shows me all the objects that are in the table, or that are in the database. So these are like the tables and the keys and stuff like that. And I can select some of the slides to show you how that works. Slides where? So these are all the slides, as I told you. So you probably recognize these titles. And I can even update one. So now I've updated it, and I can do a select again and show that it's there. And now if I go back over here, what was that? Yeah. So there I go. So I really am running this from the Gears database locally. So that's pretty cool. So I was a web developer before I started working on this stuff, and I can tell you how exciting it is to have the idea that you'll have full local storage with a database in all browsers. I mean, I think this is really cool. And again, the DB query tool that I was just showing you comes with the Gears SDK, so you can use this in your applications to experiment with different SQL queries. So the final module that Gears is shipping with is called the worker pool. And this one is really interesting. What we found when we started experimenting with taking applications offline using Gears was that, OK, now you're storing your data locally. When you're offline, you're making a bunch of changes, and those changes need to get synchronized. And when you come online, there might be a lot of new data on the server that you need to download, especially in the initial synchronization. And what happens is that, man, that synchronization code, it really chews up a lot of resources. And it makes the UI of the application really sluggish. And so we thought, well, what we really need here is a background thread. Actually, I didn't think that. The guys that work on my team that are more hardcore Windows programmers thought that. And I was like, thread, that sounds scary. And JavaScript doesn't have any threading primitives, so we would have to change JavaScript to add threading primitives like locks and synchronization, and that just wasn't going to work. And also, threading is very, very error-prone. Even very good programmers have a lot of problems with threading code. It's an area that's rife with issues. So we tried to do something a little bit better with worker pool, and basically this is a process model. So you can use the worker pool to create a background worker. And this is a separate chunk of JavaScript code that has its own variables. It doesn't share any variables with the page that created it. You can think of it like a totally separate window if you're a JavaScript programmer. And you can send messages to this worker and tell it what you need it to do. And it can send you back messages saying, OK, I did what you asked me to do, or I have an error, I couldn't do it. And basically, all the communication is done that way by passing messages. And this eliminates the need for threading primitives like locking and synchronization. And again, I'll give you an example of how this code works. Again, you use the factory object to create an instance of the worker pool. And since, like I said, all communication is done using message passing, you set up a message handler, and this tells you when something has happened on your worker. And what this example is doing is basically it's implementing the next prime algorithm, which can be very resource intensive depending on how large the numbers are. And here you can see we're doing a very large number, so this would take a long time. And this is the kind of task that you could never do before in JavaScript because it would take too long and it would block the UI. And actually, if you've ever written JavaScript that goes out of control and has an infinite loop, you know that when that happens, you can't even use your browser. You can't use other applications in your browser. You can't even use the browser itself. The browser stops being responsive. And so the worker pool should allow a lot of really interesting applications that you could never do before because the JavaScript would make the UI unresponsive. So I'm gonna show you a demo of that. So the other code talked about primes. To make the demo even harder, to be a better example of why worker pool is cool, in this demo we're gonna find prime quadruplets, which are a special kind of prime, four related prime numbers that are harder to find, and so it takes longer. It's more processing power required to find them. So I've implemented this algorithm a couple different ways. The first way is using the foreground, the regular JavaScript, just like any other JavaScript application would work. And so I started off, and it starts up pretty fast. You can see that it's going, and it's finding them. But this progress meter here shows you basically when the CPU is busy. And this progress meter is how your application would be responding if you were trying to do other things in the application at the same time. And you can see that once it gets to the big numbers, it's really not, this progress meter is no longer smooth. It's really chunky. And this is not good. And if I was trying to use my browser at the same time, I'm going to start trying to tab around, and you can see that tab isn't really working anymore. I can't really, I couldn't really use my browser for anything else while this was going on. And this is a horrible experience, and it's one of the major limitations of JavaScript development. So now I've implemented the algorithm the exact same way. It's the exact same code. It's just running in the worker pool now. So I start it up, and again, it starts out fast, but once it gets to the bigger numbers now, you can see that it doesn't affect the progress meter at all. It just keeps going totally smoothly. Well, in the background, the CPU is just spinning and spinning, trying to find these primes. And I can start using the tabs, and you can see that it's totally smooth. My browser is still responsive. And I can even start up another instance of the code. They can both go at the same time. And I can still use the tabs. So I think this should open up some really interesting possibilities. So this was going to be the end of the presentation. It was going to be the end of the presentation, except for we were joking around the office that, man, it doesn't have search in it in any way. And we were sort of afraid that Larry wouldn't let us launch it if it didn't have search somehow involved. So I added a little search box here to the presentation, just for fun. And I'll type in full text and see what it says. And it found another slide. So we have a bonus slide here. Yeah, so while we were working on Gears, we started a joint project with the people who run SQLite to add full-text search to their database. So prior to our involvement, SQLite didn't have a full-text system, which means that you can't do the kind of searches that you can do on Google.com. You can only do structured searches. And so we thought, well, we know a little bit about searching, so we'll add that to it. And so the project we started, it's called FTS2, which is a very creative abbreviation for full-text search 2. And that one is in Gears today, and you can use it today for whatever applications you use Gears with, and it scales to millions of documents. But we thought, that would be cool if it could go bigger, so we started a new project called FTS3, which we're working on right now, and isn't available in Gears yet, but it's being done completely in the open. So if you're interested in that sort of thing, you could follow the mailing list and see it. And that one will do tens of millions of documents. And it will do multilingual search. So you can search in French and Chinese and Japanese or whatever if you speak those languages. So just to recap what Google Gears is, it's a browser extension that enables offline applications. It runs on a lot of major browsers, i.e. Firefox on all the platforms that Firefox supports. And it will run on Safari. We have the code checked in, but it's not quite ready to deploy yet. It's an incremental approach to the offline problem. Instead of completely redesigning the web, we like the web the way it is for the most part, and we thought we would just add key pieces to make applications work offline. And again, it's a very early beta release. You can start building applications with it and tell us where it's broken, where it doesn't work, and we hope to iterate very quickly and be responsive to what's needed. So that's it.